Thanks a lot to Houssem for giving a talk. We're very happy to have Houssem Haddar today, which will be talking about a duality between invisibility and resonance with some applications. So thanks, Houssem, for coming.
So thank you, Knut. Thank you, Katja, also for this invitation and give me this opportunity to present so this work, which is a common work with Fioral Bazzaconi from Rutgers University and David Colton from the University of Delaware for the first part, and there will be a second part, which is a collaboration with people in Paris, Lorenzo Dubert from EDF, Lucas Chanel and Kevish at INRIA. So my talk will be divided into three parts. So first part, which is just some general comments, motivation behind what I want to present. And then, so there will be two parts related to so the works with these collaborators. Okay, so let me start with some general motivation and context of this topic. So the application we have in mind is related to inverse scattering, and typically the situation where so you have some measurements, here multistatic measurements, so many sources and receivers, and you like to probe some complex domain that is difficult to model. Okay? So you don't have a forward model, and you want to probe the presence of some defect or monitor the health of the material inside this domain. And so what I will present is some idea to tackle this type of inverse problem where you have very few a priori knowledge. Okay, so the main thing is that, okay, we have no forward solver and maybe we need sometime information of the scatter location. And okay, so the applications that can be like this are, for example, you want to find cracks in some concrete, or want to monitor the health of some composite materials, etc. And I will present some application for example, try to identify some criteria related to crack densities. And okay, so for this, we would like to build what we call some qualitative indicators. And these qualitative indicators will be some spectrum related to the inverse scattering problem we are interested in. And in the literature, there are many that have been introduced. And so the one that is at the origin of this type of idea of you building this qualitative indicator are so-called transmission eigenvalues. Okay, and these eigenvalues, these are the one that is related to invisibility, which is part of the title of my talk. And to define them, so we can say that these are the frequencies for the forward problem for which you can build some incident field that do not scatter. And let me just give some illustrations. So for example, in the case of a circle here, which is inhomogeneous, and if we take the frequency k here, so it's a special frequency. Of course, if we send any point source wave, you can see it in here, we obtain a field here, which is called the total field, for which there is something that is scattered. So what is outside the scatter is what we call the scatter field. So there is, you can see the influence of this inhomogeneous media. Now, if you do a special combination of these point sources and you build this type of incident wave, so this solution in the homogeneous space, you can see that, so we obtain some perturbation, but if we see the scattered field, you can see that it is exactly zero outside the inhomogeneous media. Okay. And so, in fact, what we can prove is that this can happen only for a given inhomogeneity. This can happen only for a set of specific frequencies that form a discrete set without finite accumulation point. And these frequencies for which you can build this invisibility. In fact, you can see that inside the inhomogeneity, so the field is, the scattered field is really confined inside the scatterer. So it is related to some kind of resonance inside the scatterer. So invisibility outside is related to resonance inside, and this is what is referred to in the literature as the inside-outside duality. Okay, so this is the first remarks, that there is some resonance that we will characterize later in the talk. Okay, and moreover, so since they are related to something happening inside the scatterer, means that they carry information about the material properties or also the shape of the scatterer. And this is what we will try to exploit later when I will introduce some indicator function for crack densities. And the main thing is that there have been methods that are capable to determine these special frequencies from measurements outside, and this is also what I will present. Okay, the other set of special frequencies for the scattering problems. So these are much more older notion and much more studied quantities. They are called the scattering poles, and they correspond to meromorphic extension of the solution operator to the complex plane. Okay, and so they come with the non-negative imaginary part, and they can have also a physical interpretation, like, for example, they are related, so the distance determine to the real axis determine the rate of decay in time of the scatter wave. So there has been an attempt to use them for the inverse problem, but it's very difficult actually. Okay, so this, and in fact, what I want to discuss here is some duality between these scattering poles and the transmission eigenvalues. So if we try to define differently these scattering poles, in fact, they correspond to the complex, so to some frequencies, they are complex in here in the sense they have non-zero imaginary part, for which there exists non-trivial solution even with zero incident field. Okay? So if I put this into perspective with the transmission eigenvalues, so these are the frequencies for which you have non-zero incident field but zero scatter field. So there is some duality, and the thing is that, so I said transmission eigenvalues, invisibility outside, resonance inside. So here, this corresponds to some resonance outside. And what I want to explain is that, of course, so using this duality means that the scattering poles that can be also interpreted as some invisibility for an interior problem, for inside. So this will be one of the objective of this talk, and if I have time, I will also talk about this identification of crack densities, because in fact recently we also developed method to generalize this notion of transmission eigenvalues, and in fact it turns out that we can build infinitely many spectrum. And so some of them can be more suited to some inverse problems, and I will give some application for the cracking again. Okay. So this is the general picture of, let's say, what has been done in the literature. And my talk today, so this is what I want to present in the technical part. So there will be a large part dedicated to discussing this duality between transmission eigenvalues, scattering poles. And the main thing is here that, okay, relating scattering pole to some invisibility for some interior problem leads, for example, to a numerical algorithm to determine these quantities. And okay, I will discuss them for this very simple example of Dirichlet obstacle, where things are more or less obvious. And then, so quickly also say a word about the case of Penetrable Media, where the interior problem is a little bit different. And then in the second part, I will discuss applications of this inside-outside duality for cracks. And okay, the main trouble there is that for cracks there is no interior, so we have to do something else, and this is where the notion of artificial background comes in. Okay, so let me start this first part, and this first part is mainly based on this paper with Albert Sakon and David Cole. Okay, so to discuss this duality, let me, I need first to properly define these quantities. And so this is why I will try to do it a little bit slowly. So first, the first object that needs attention is the so-called fundamental solution to the Halmos equation. So I'll just write it in here because it will appear in many instances. And so this fundamental solution is related to, okay, this expression with the plus sign in there is related to the Sommerfeld radiation condition that uniquely determine this fundamental solution. Okay? And with this radiation condition, we can set up, so classically, the scattering problem. So I'll consider here the case of point sources. So considering incident field that are generated by point sources, we can formulate the Dirichlet problem as the following. So you have a delta function at the point x0 where the sources is, and you have some Dirichlet boundary condition on the boundary, and okay, defining the scattered field as the difference between the total and incident field, you can set up this system for which there exists a unique solution. So this is very classical. Okay, and in fact, you can reformulate it. This is more generally by replacing here the incident field by any boundary value f, and so this defined well-posed problem. Okay? So, and it is well posed for all frequency k and even complex frequency, but with a non-negative imaginary part. Okay. So, and this causes trouble because I said, okay, for resonance, all poles of the scatter makes, they correspond to non-trivial solution for zero data, and so I said that it is well posed over here, but in fact so the known well posedness comes from the extension of this problem to the case of imaginary of k negative, and for this we need to, of course, if we want to extend, this condition no longer holds, and we need to modify this condition, and so there are many ways to do that. And the way that allows us to prove things later is the following. So in fact, it can be proved that, so this is also very classical, is that the scatter field can be represented in terms of potential on the boundary of the obstacle. And now the importance of this is now explicit in terms of the frequency that is hidden in the phi, okay, I introduced it. And this expression for phi is analytic in all of R3. And so you can extend now this condition to the whole complex plane, and then you can reformulate the scattering problem as the following. And what we can prove is that it is of Fredholm type for all values of k, and so it is invertible except for a discrete set of frequencies, and the set of these frequencies should lie, of course, in the negative half complex plane. Okay, and so these frequencies, this is what we refer to the scattering poles, and so they correspond to the notion of resonance, because putting f equals 0, we have a non-trivial solution. Okay. And okay, since I would like to present some duality between exterior and interior, so let me refer them to the exterior resonant frequencies. Right? So it means for the exterior problem. And again, so I already introduced the notion of transmission eigenvalues. They are related to invisibility. So there is some data that produce zero scattered field, and I will call them in our in the context here as interior transmission eigenvalue. So these interior transmission eigenvalues, they are the frequency for which there exists a scatter wave that is zero for non-zero data. Okay, and okay, the duality I want to express is, of course, this is well known that interior transmission eigenvalues are related to some interior resonance. So transmission eigenvalues is some resonance. And so what is somehow new is that exterior resonance, so the similar way, can be also viewed as invisibility, but for some interior problem. I have defined scatter pole. Let me now define this interior transmission eigenvalues more properly, because in fact, so this formulation is not really suitable to define properly these transmission eigenvalues, because you see, if the scatter wave is zero, the data should be zero. So we cannot really define the notion of invisibility by formulating this the scatter problem as like this. In fact, to properly introduce these transmission eigenvalues, we have to go back to the scattering problem. Okay, so I have to go back to this scattering for point sources, and okay, so this is just a reformulation of the problem I mentioned before. Okay, so this will pose for imagine of k positive, so we are not hitting these resonance frequencies or scattering point. And okay, so I can define for each point source this scattering field, and now what I would do is combine these incident waves. Okay, so if I combine these incident waves, okay, with some density g, so I put these sources into on the boundary of some domain that encloses the directly obstacle or obstacles. Okay, I combine them with some density g, and this gives me more rich like family of scattered waves. Okay, where the data now is the trace of this type of okay, Hercules-like wave. Okay, so this is a singular potential. And now, in fact, I can define now the invisibility occurring when I can build a sequence of density g, okay, for which the scattered wave goes to zero. Okay. So if the frequency k allows me to build a sequence of g, and for which, so I should be more specific because this is a compact operator. In fact, I need this sequence to converge to some non-trivial function inside the domain D. Okay, and of course, to have invisibility, the scatter wave should be zero. So the scatter wave will be related to the trace of v. So means that v should be zero. So if these k exist, they should be such that the function v, okay, so inside D, this is the limit of some singular potential supported by a boundary outside D. So they satisfy automatically the Halmos equation. And since the scatter wave is zero, because this is for the Dirichlet problem, this means that the data should be zero. This is what I said. So you obtain that, of course, so you have quasi-invisibility for this combination of point sources. Okay. If you can build that only if k square is an eigenvalue of this interior problem. And in fact, we can prove that this definition is equivalent to the fact that k is a Dirichlet eigenvalue. K square is a Dirichlet eigenvalue for negative Laplacian in D. Okay. So what? Okay, so here you can say, okay, so this is really a very complicated way to just define the Dirichlet eigenvalue for the negative Laplacian D. But in fact, this way of definition allows us to build an algorithm to recover these values only from measurements outside D. Okay, so these sources really, okay, let me go back. Okay, so these are point sources outside D, and now we will measure also outside D, and we will be able to recover these specific quantities for the domain D from only measurements outside. Okay, and that has been okay. So this is this is just the setting. Okay, so consider now the scatter waves that comes from point x0. We can define this very simply, this operator. Okay, that so here you see we measure on the boundary of B and point sources on the boundary of B. We build this so-called near field operator, and this is how we can recover these special frequencies, the theoretical eigenvalue, from this measurement operator. Okay, so this is inspired by some work that we did with Lorenzo Odiber on so-called generalized linear sampling method. So the idea is the following. In fact, it is inspired by this limiting process to build this invisibility. And now, in fact, we will, what we want to do is the following. So we want to build a nearby solution to this equation. So we want that n of g be equal to some data, and this data corresponds to the point source at the sampling point z that we will put inside the domain D. Okay, and this may not be exactly solvable, and so we, in fact, this operator has dense range, so you can build a minimizing sequence, but we want to control this. For this sequence, we want to control not the norm of this density, but the norm of the generalized incident wave. So this is where it should converge, I said, for the invisibility. So now, in fact, you can prove that if you are not at this Dirichlet eigenvalue, then this quantity as, okay, so here is just to say that I'm building a minimizing sequence. Okay. So this quantity will remain is bounded for all points inside the domain D. So you need to know, it's where you need to know the domain D. Okay. While if you are hitting these special frequencies and under some extra assumption that, okay, so I can come back later to this if you have questions. That so this means that basically the solution, the Dirichlet eigenfunction, is not of the form exactly of this form. Then we have the converse of this statement, in the sense that the point z for which this quantity remains bounded is nowhere dense. So meaning that this will explode almost surely. And so numerically, you can how you can identify these special frequencies. It's enough to let's say, so to build this function. So you just compute these quantities for a bunch of z's inside D, and you take average values. So this, since this blows up, it will have peaks at these special frequencies. Okay, so and in fact this works quite well in some and in some early works. We said that okay, we can even use these to have some idea on some defects that occur inside the domain. So let me just, to give a break with some numerics, give you show you how it looks like. And in fact, in this criteria, you can even numerically replace this quantity by only the norm of the density, and it works. So we cannot justify it, but it works also. And so, for example, here, in fact, I present this for penetrable media, but the idea is basically the same. And so you obtain, of course, so the solid line is this function k terms terms of this quantity, and the circles, these are for the analytically computed values. Okay, so let's say directly eigenvalues. And in fact, for the penetrable media, you can see that if we add some defect here, it's a cavity, this will change the spectrum. So see there is a double eigenvalues here, it becomes 1. And even if you increase this, the radius of this defect, there is a shift in this spectrum. So this is where it comes the idea that, okay, given these special frequency can be of interest for the inverse problem or for the inverse spectral problem. So since they carry information about the index of refraction or some defects inside the medium. Okay. So as I said, the main objective of the talk today is to say that, of course, what we can do for the exterior problem, we can do it also by reversing the exterior and the interior. And we should also reverse the notion of scattered and incident fields. Okay. Now, for the interior problem, okay, so to reverse that now, I will put sources inside my domain, and I will consider now the interior problem. So it's the same Halmos equation. It's just that I'm rephrasing this in terms of, you can see, so this is the incident field that now plays the role of the scattering field inside. And now, if I am not at a directly eigenvalue, so here it is sufficient to have some imaginary part that is non-zero. So this is well-posed problem. I can define everything nicely. And as for the exterior problem, I can take combinations of these point sources with some density G. So this gives you some field inside related to these data. And I can define also some invisibility now. So saying that, okay, so I will be invisible for the interior problem if I can build a limiting sequence for which the VG is 0. Okay. So this is what it says in here. So, okay, I can define now this, it's kind of transmission eigenvalue, but now it's exterior transmission eigenvalue because it's related to some exterior resonance. So the exterior transmission eigenvalue will be the values for which you can build some sequence that converges to some W outside the domain D, for which if you solve the interior problem with this data, W, you obtain 0. Okay. So in fact, this means that this W should be also 0 at the boundary of D. So that's why the directional problem is kind of trivial in here. But what is important to prove is that, of course, it solves the Halmos equation because this solves the Halmos equation, but it should be also satisfying this kind of radiation condition. And this is the hard point, actually. This is why we needed to reformulate the problem in this way. And so this is the main theorem. It says that these exterior transmission eigenvalues that corresponds to some invisibility are exactly the exterior resonance frequencies for the Dirichlet problem. So they are the scattering poles. And so once you realize that, then you can also try to do the same for the numerics. And okay, you can, for the numerics, what you can do is just, so you forget about D, you just take some measurements operator inside. So you solve for a bunch of point sources in here, you build this operator, and then you can do the same now. So you take this interior measurement operator, and you penalize now with some norm. So it's like H1 log. So this is some domain that encloses D. And so this is the correct penalization, and you obtain basically the same type of results as for the exterior problem. So if you are not hitting the scattering poles, then this quantity is bounded as alpha goes to 0. So for this minimizing sequence, and under this extra assumption, if you are now hitting scattering poles, then this quantity will close up. And Okay, so this is like what should be for the Dirichlet problem. Unfortunately, we are not we do not have time to do numerics. So this is really so will be the so the next to do for this problem. Now, okay, let me discuss the case of penetrable media, where things are a little bit different, but basically the same ideas apply. Okay, so for penetrable media, we have it is defined by the index of refraction here. So I take this setting where okay, we have Halmos equation with an index of refraction defines in all of R3, and we can define so scattering for point sources by so consider this equation with some radiation condition. Okay, so it can apply to the scattered field. Okay, and in fact, so for the scattered field, we can reformulate it. We can reformulate the problem as the following. So I'm just doing this quickly, but it's just a rewriting of the equation. So the scattered field is solution to this type of problem. So W here plays the role of the scattered field. Now it's in H2, and so the incident field is encoded in this function V. And similarly to the case of the Dirichlet problem, I can encode the radiation condition in terms in this representation of the scatter field outside the domain D, where so the domain D is now the domain is the support of n minus 1. Okay, so n equal 1 outside D. And in fact, with this formulation, we can prove that it is equivalent to reformulating the problem in terms of Lippmann-Schwinger equation, which gives that, okay, Fredholm, so the fourth problem is of Fredholm type of index 0, and so you can have meromorphic extension of the inverse. Okay? And so the set of scattering poles in here also form a discrete set without finite accumulation point. And okay, now we can do we can try to do the following. So for the invisibility is the same. Now the only difference is that now you see here depends on the problem, but now we reformulate the convergence in terms of L2 of the domain D for some limiting. Okay, so combination of incident waves. And what we obtain now, so what we want is that this combination give rise to zero scattered field. So if W now is 0 outside D, okay, I obtain this set of equations. So this equation is for the incident field, which is limiting, which is limit of these functions that satisfy the Halmos equation. And so this is just the equation for the scattered field in terms of the incident field. Okay. So what we obtain in this case is a coupled problem, and this is the celebrated transmission, interior transmission problem, where the unknown now is L2 function for V and H20 of D, because now W has H2 regularity and 0 outside. So we obtain now some kind of resonance, but for some coupled problem. Okay? And so there has been rich literature on this, on the study of this problem in recent years. And in fact, what the main difference with the Dirichlet problem, or the obstacle problem, is that now we have non-self-adjoint so a non-self-adjoint spectral problem for which there may exist complex eigenvalues. Okay, so this will cause us trouble a little bit later. And in fact, so you can see that this is even a quadratic eigenvalue problem. Okay, for those who does not know about this problem. So here we just, if If this is invertible, you just divide by this, you apply this operator, you obtain this quadratic problem. So, okay. So this slide just to say that, okay, so we can say something about the transmission eigenvalues for this problem. For example, if this contrast does not change sign, there is infinitely many real transmission eigenvalues that we can recover from measured data. But this fact is not proved in other instances, for example, where n, where this contrast changes sign. And this is one of the open questions for this problem. Also, existence of complex transmission eigenvalue is not known. Okay, and we just finished writing with Fioralba and David some review of very recent results about this problem. So it just submitted. Okay. Now, what I want to discuss is how we can extend now the invisibility for some interior problems so that we can recognize scattering poles for this setting as transmission eigenvalues for some interior problem. Okay. Here I choose to reformulate the problem, maybe because it's more clearer. I go back to the formulation in terms of total and scatter field. In fact, so the total field U will be the sum of W and V, and you can reformulate this problem as this coupled problem with coupled on the boundary. Okay. Because now for this allows me to introduce the interior problem, where we will now put data, but put data not only for U and V, but also for the normal derivative. Okay. Now the interior scattering problem is amounts of solving this coupled problem inside the domain D. And what we can prove is that if you do the same thing as before, now consider this combination of incident waves. Okay, so you can build now the interior solution to the interior transmission problem. Now, to do that, of course, you need to avoid the k-square to be an interior transmission eigenvalue. Okay, and of course, now, as I said, the interior transmission eigenvalue for this setting can be complex. So one of the questions that we don't know is, okay, can we hit at the same time an interior transmission eigenvalue and a scattering pole? But assume that now we exclude the interior transmission eigenvalues. Now this problem is well posed. You can build this solution, and now you can define invisibility as the so the sequence Gn that will form some data that I call W in here, that will live outside D, so it should be non-trivial data outside D, for which I need now the incident field to be 0. Okay, so the incident field for the exterior problem. And what we can prove is that these once again, so this is an equivalent definition for scattering poles. Okay? So defining K this way, or defining them as being the K for which there exists non-trivial solution to the exterior problem is equivalent. And okay, I end up with just reformulating the same theorem, but okay, now here, so some just technical details differ in, for example, in the penalty term. So basically here, the main trouble is that we need to assume that K is not an interior transmission eigenvalue. And so we will recover only the scattering pole that do not coincide with those. Okay, so I end up with this, what I wanted to present about this duality. And once again, so the main technique part is in this paper. In the remaining of my talk, I want to present a different application of this duality between invisibility and resonance for the crack problem. And this is some work that has been done with these guys. Okay, it gives you an idea also on how we want to apply these, let's say, spectrum to obtain qualitative indicators for some inverse problem. Okay, I have 10 minutes to do that, so I'll try to be quick. So the problem here is the following. So assume that you have fracture media, but where you have many cracks. Okay? And the cracks, they are closely spaced and very dense, so that if you apply, like I say, any conventional imaging technique where the wavelength is comparable to the size of these cracks, you will obtain some blur image of the region where the cracks are dense, and you can possibly identify the cracks that are outside this dense region. Okay. So this is, for example, what we obtain with two different sampling methods, but I would say that you can obtain even other type of other imaging technique, you obtain similar results. So the idea now is, okay, for this inverse problem, I'm not really interested in knowing exactly the geometry of these cracks. What I want to know is information about the density of these cracks. So to have an assessment on the health of the structure. Okay. So can we do that? Yeah, so what we tried is to come up with some idea to do that based on these transmission eigenvalues. And of course, there is a little bit contradiction between transmission eigenvalues and cracks, because I said transmission eigenvalues are related to some interior resonance, but for cracks there is no interior. And this is where comes the idea of using some artificial background. So we will artificially introduce some resonance by introducing some artificial background. And so the idea is very simple, okay? And this is summarized in this slide. So here's the domain with cracks. So for which, okay, here the cracks are modeled by some Neumann boundary condition, but you can put any boundary condition you want, in fact. Okay, so this is some model for the true problem. Okay. And I assume that I have some measurements for this problem. Okay, now for simplicity, I just take the case of homogeneous media. And what I will introduce is some auxiliary problem that I built on purpose. And so for the numerical example, it will be built numerically. So I just take some domain D. Okay, so this I choose to be a circle for simplicity, and I take just the scattering problem, the same scattering problem for the same incident wave, okay, but for the case where D is a Dirichlet obstacle, okay, plugged into the homogeneous. And now the question, I can rephrase the question I asked for transmission eigenvalues here, similarly in this case, by trying to find some incident wave, okay, using some limiting process for which the scattered wave coincide for this configuration will coincide with the scattered wave of this configuration. And this is some generalization, because in fact you can see that if D is empty in here, the scatter wave is 0, and so it's exactly saying that US is 0 if there is no D. So I'm replacing 0 incident field by 0 scattered field by scattered field being equal to some reference scattered field. And of course, you can do this with Dirichlet obstacle, because you have the freedom to choose any reference media. And this is why, so there is some flexibility in this notion. Now, of course, now if I merge the two media together, so I put the domain D with the crux. So in fact, it's easy to see that imposing this equality between the scalar fields means that k square should be an eigenvalue for the negative Laplacian inside D, but also outside the crux that intersect the domain D. So once you realize that, so then the idea is very simple. Okay, so here I can define now what we call some relative transmission eigenvalue relative to the background I choose. So these are the eigenvalues for which this problem has non-trivial solution. Okay, so it's just the red circle with the crux. And of course, in the paper, so what I'm not showing here, so we can do the same analysis. We can reconstruct these values from the differential measurement operator. So I take just the difference between the operator that is built from the measurements for the crux and the operator for the background that I can build numerically. So if I take this difference, assuming some assumption, we can prove that in the similar way as I presented before, we can reconstruct these transmission eigenvalues. And of course, given this structure, it is easy to see that there is some monotonicity with respect to the size of the crux inside D. So if the size of the crux increases, then the eigenvalues for this problem decrease. So there is some dependence on the transmission eigenvalues with respect to the density of crux. And so this is what we exploit in the what we propose as indicator function. So what you will do is just you can take your domain that have given size and you move this domain inside the probed domain. And if there is no intersection with the crux, you obtain just the Dirichlet eigenvalues for the domain D that you choose. And so if it intersects a lot of crux, you will decrease much more than if it intersects one crux. And so this is basically the idea that has been implemented. And just to finish with some numerical results from this paper. So you can see that if we apply this, and even if we use only one eigenvalue, so the first, and we compare the first transmission eigenvalue with the first Dirichlet eigenvalue. Of course, we choose D as being a circle, so numeric is very easy to compute the background operator. And the size of D, in fact, will tell you which frequency you should look at. So because it depends, it determines the first Dirichlet eigenvalue. And so this gives you the resolution of the method. And you can see that here we obtain, of course, not the shape of the crux, but a better indicator on the density. Okay, so I think I'm almost in time for the 50 minutes. Just some conclusion with some perspectives. So there is, of course, I said that we obtain a new numerical algorithm for scattering poles. So we should really test the efficiency of this numerical algorithm, even though I found that this remark between this duality is interesting on itself. And of course, there is this question that seems to be hard to answer. For the case of penetrable media, do anterior transmission eigenvalue intersect with the scattering poles? Of course, okay, so this is more a technical point that we really want to answer is, So this injectivity, of course, there are a lot of work that has been done to prove the injectivity of these measurement operator at transmission eigenvalues. This amount to see whether you can represent the solution to this interior transmission problem or for the Dirichlet eigenvalue as singular potential or as Hagel's wave in some other context. And so, for example, we know that if there is, so there are work that said that proves that if there are corners, this cannot be the case. So it would be interesting to see this also for the scanning poles. And for the numerical algorithm, it would be interesting to avoid this assumption, because even if it holds, even if the operator is not injective, we observe numerically that it works. And for the last problem, so there is, I just presented a way to choose the background so that we obtain an indicator function for the cracks, but there are better ways to do that, where you encode the spectral parameter not on the frequency but on the background you choose, and this can be more efficient numerically and also for application. Okay, and thank you for your attention. I think I stop in here, and if you have questions, it's my pleasure to answer.
Well, thanks a lot for a great talk, Houssem. So the floor is open for questions now. So please unmute yourself if you have questions. So I'm just wondering for this crack inverse problem. So when you have this Dirichlet obstacle, you vary the size of it.
So we keep the size fixed, and we just move this obstacle in the probe domain. So the idea is that when you move this obstacle, at some point it will intersect with cracks. So the eigenvalue will become the eigenvalue not for the empty domain, but for the domain with crack inside. So we'll shift these eigenvalues. And so we measure this shift. So as you move this obstacle, and the shift will be larger if there are more cracks inside the domain. And so basically, you can see here in the, so what we do in here, so we choose a circle, which is, okay, size 0.1, but we move, so here the distance between points is only 0.01. So there are intersections. So we just sample, but the domain D will contain, may contain the same cracks when it moves in here. So what we measure is only the shift between the transmission eigenvalues gives you, okay, so we can prove that it is related to the number of cracks. So if the shift is bigger, means there are more cracks inside the domain. And this is what we observe here. So if the circle is in this region, it contains more cracks than if it is in here.
Right. Yeah.
So basically here there are no cracks, so you can see that, yeah, the difference is 0.
Good.
Hi, just a very quick, stupid question. First, thank you for your talk. In the left image here, why is it coarser than the other two?
Yeah, so because of the because of the procedure. So as I said, so here, so what you can see is that just that pixels actually what. So here the center of the pixel is the center of the circle here. Okay, so let me move back. So we have a circle here with some center. So we just move a center into some grid. Okay, and the grid is these square. So the distance between two different points is the size of this pixel you can see in the image in here. So for each point is a position of the circle, and for each point there is a value, and this value is this difference. the difference between the transmission eigenvalue we compute and the transmission eigenvalue for the empty disk. So this is why you obtain just this pixelized image. And so this the color here is just the value of this quantity.
Thank you.
Of course, you can refine better, but I don't think that. So there is. Okay, this is what we want to understand really, is that, yeah, so what is the, okay, you can decrease this, but then what would be, does this improve the quality of the results? I'm not sure.
Thanks. Still other questions for Houssem?
Okay.
Also wondering, so in this crack inverse problems, would it be, you know, what would be the effect of polarization if you have measurement of polarization? Could that help you?
What do you mean by measurement of polarization? Like, so, oh, the polarization, that's for I'm not sure I mean, so for this configuration of the crack, I mean, whatever you use as inversion method, there will be so much multi-scattering that it's impossible to get any exact reconstruction of these. Okay.
Right.
Okay, now the only what you can yeah, for example, if these are small cracks, you can try to homogenize and obtain some equivalent material and then try to recover the variation of this material. But here, so what we do is does not need that. It's so the cracks can be very long, can be whatever. It's because what is important is that, so the size of the disk you will need for your numerical. So this, in fact, the size is determined by the range of the frequency you have, because the transmission eigenvalue should be in the range of the frequencies you have in your measurements. And so this is related to the size of the domain you should use. So there is, so this determines of the resolution of your somehow of your inversion method. And of course, in here, we do not need this smallness assumption for the cracks or any limiting regime or any asymptotic regime.
Great.
Anyhow, so if people have questions, then you can send also email to ask questions.
Yeah, well,
happy to answer.
Great.
And so if I understand, so the slides will be available online. So
yeah, thanks a lot. Thanks again for a great talk, Houssem. And
thank you for the invitation. So
we'll, as Houssem mentioned, we'll put both the slides and also the video on the online, so you can follow up and look at what was presented again. So thanks a lot for the talk, and thanks to everyone for coming.